Hello, this is Jitterwagen, and this is the first video in a series of videos in which I will be introducing QGIS 3.4 long-term stable release. In this first video, I will be talking about basic actions in QGIS, such as opening and simple editing of typical GIS data and visualizing this data. Okay, I will start this introduction video with explaining the QGIS desktop interface. Here at the central area, we now see recent projects, but if we would start a new project or open an existing project, this actually turns into our map canvas. This map canvas is the area in which all the data that we will add to our GIS will be visualized, and we can do basic manipulations with that data. So below the map canvas, we have some pieces of information referring to the information in the map canvas. The most important being the coordinate location of the cursor, the scale at which our data is displayed, a magnifier, a rotation of the map data if that for some reason would be different. You want to have it different than the default north orientation of your chosen coordinate reference system. You here have the option to temporarily switch on and off real-time rendering of your data, which can be useful if you have very heavy information in your map that makes every single small move very hard for GIS to real-time render, so it takes a long time to load all the data, so you can temporarily switch it on or off. And then finally we have here the EPSG, so the European Petroleum Search Group ID, which refers to the coordinate reference system. And we'll come back to the concept of coordinate reference systems in detail. So to the left of our map canvas we have two windows, the upper one being the browser window, the lower one being the layers window. And we can use the browser window to access all the GIS data files on our hard disk or on other locations such as data portals, online data portals that we can access via the various entries over here. If we would open a GIS data file, it would visualize here in the layers panel as a layer which also will display in our map canvas, of course. I will open a data file just as an example. And in order to do this, I will browse to the training data for this introduction video, which you can do in a simple way by opening and browsing through your folders. And I will select a data file, which in this case will be ahn3 uitsneden.tif. And this is the LiDAR data collected by the Dutch government of the Dutch landscape. And you can see I just drag it from the browser panel into the layers panel, and there it visualizes as a layer with a symbol referring to the data type, which is a raster file. I see the lowest and the highest value of data available in the file, and it's visualized in my map canvas. And now suddenly we see coordinates that might make sense, which are coordinates referring to the Dutch grid, which now also through the EPSG ID here is visible, which is indeed Amersfoort RD new 28992. Now at the top of the interface we have a few toolbars with buttons and the actual menu in which you can find practically all the options and possibilities and functions that QGIS offers. I won't go through all of these in detail, and we'll discover the function of a lot of these functions as we progress through videos. What I do want to show already though is how you can switch on and switch off specific panels and toolbars in case you use them a lot and want to have them easily at your disposal. If you select the menu option View, go right to the lowest part of the menu, you can either select panels or toolbars. And I personally personally like to use the Manage Layers toolbar, and here you can easily switch it on and you'll see that a toolbar appears that you can use directly instead of going through menu options. Okay, so as a first step in this introduction on QGIS, I want to show how you can open various GIS data files in QGIS. So I already opened this raster file. I mentioned the file type. So maybe this is a good moment to very briefly explain the difference in file types that you can have in GIS. At least the difference between the two major ones, which are raster data and vector data. Okay, so the raster data that I already opened here must be seen as a grid of equally sized cells in which every cell can have a single or multiple values. And this is determined by the number of bands that the raster actually has. So every cell can contain one value if this is a single band raster, or it could contain 3 values in a multi-band raster, each band having its own value. And typical uses of raster data are what we have in this case, which is a digital elevation model in which every cell has a single value, in this case representing an elevation. And as an example of a 3-band multi-band raster, every cell could store, for example, in every single band an RGB value. So 3 values that, of course, creates a color, and that would be typically used to visualize an aerial photograph. Now, the other data type that I named is vector data. I will open a file with vector data here indicated by this shape over here to demonstrate how vector data looks like. This is a polygon layer, and vector data consists of geometrical descriptions of spatial information, and this practically comes down to coordinates that are connected. So if there are 3 types of geometries in vector data files. If you have a point vector file, you have just coordinates. If you have connections between these points, vectors, you have a polyline layer file. And if you have connections between these points where the end comes back to the beginning, you have a polygon vector file. Okay, so when do you use vector data? As you may already see from the vector data that I added, vector data is very precise due to its definition in terms of coordinates and connections between coordinates. So vector data is best used for discrete information. So, for example, as it is used here to indicate where there is a road or a parking area and where is not. Raster data, on the other hand, is most suited for continuous data, where you have a continuous variation in information in the whole area, such as minute changes in elevation in this case. Okay, so the vector file you just saw me dragging into the layers panel had this file extension .shp, which is actually the native file format of Esri's ArcGIS, which is another GIS program. And you can open that without any problem directly in QGIS. On the other hand, I have here another file format, which is actually being recognized as a vector file format, and hence the symbol. But it's of a different extension. The extension is .tab, and this is in fact a MapInfo vector file. Now, of course, this is similar to raster data files, in which you also have, of course, different file extensions, different file types that store the same kind of information, but just differently. But to go back to the TAB file, MapInfo TAB files are not immediately completely recognized by QGIS, in the sense that the coordinate reference system information is directly recognized. And what I mean by that can be seen if I would open the TAB file directly in QGIS. So I drag it into the layers panel and I immediately am confronted with this coordinate reference system selector. Now, what I have to do here is specify in what coordinate reference system these data have been recorded in the TAB file, I mean. Now, before I go and show how you make the right selection and display them on the right location, just very quickly about coordinate reference systems. So about a coordinate reference system, a coordinate reference system consists of a datum and a projection. A datum refers to a system in which you can define positions on a globe. So a 3D position on a three-dimensional globe or sphere, so to say. And a projection system is a way to project these coordinates in a 2D, two-dimensional Cartesian system. And you can imagine that if you have points on a globe or on a sphere and you have to project them onto a flat two-dimensional surface as we do on our screen in a GIS program, there will be a deformation of some kind. And this is why you have many different projections respecting different aspects, spatial properties of your data. And so the combination of having different datums, the one we use most of the time is the WGS84 datum in combination with some sort of projection, but because we have a couple of datums and very many projections, a coordinate reference, there are an enormous number of coordinate reference systems, and it's very important to choose the right one for your data. So that is very briefly on coordinate reference system. Now what happens here is I add the TAB file to my GIS. It has coordinates, so QGIS sees that it has coordinates, but these coordinates can mean different things in different datums and projection systems. So what QGIS now wants to know is, okay, I see these numbers, but how do I have to interpret these numbers? Where do I have to position this data in relation to the data that is already in your GIS? And this is why we are confronted with this coordinate reference system selector. Now we can do a couple of things here. We can use a filter to search for the right system, because as I said, there are an enormous number of different coordinate reference systems. We can select recently used coordinate reference systems, or we can browse for coordinate reference systems, in which case this screen quickly becomes too small to adequately see all the possible options. Now, so apart from being able here to choose 28992 EPSG, because I already used it before, you could just, if this is the first time you open it and you're not confronted with any recently used coordinate reference system, look for just type in the EPSG ID and you will be offered the option of Amersfoort RD New as well, or you could just filter on characters. So if you select this coordinate reference system and you hit OK, then you will see that our data, in this case referring to identified features in archaeological test trenches, is actually being projected on their right locations. And if you would have chosen another system or no system, they would not have appeared on their right location as they have been here. Okay, so what is useful to know about these coordinate reference systems is that you can set also a specific coordinate reference system for your project. Because what happens here is that QGIS is by default set to take for the project the coordinate reference system of the first layer you add to the project, which in our case was the AHN raster, which was already set to the Dutch grid. But it may be that you want to work in a different system and you just want all the data to be projected in the right way in that system. Now here you can go to settings in the menu and to options. And then in the options window you can go to the CRS tab. Now as you can see here, CRS for new projects was set to use the CRS from the first layer edit. But you can also just say, I want to use a default CRS. Now that can be useful if you have a specific reason to work in another CRS than your data is projected to. It can also be that you have data projected in various coordinate reference systems, and other than reprojecting that data, which is a possibility and something that we'll do in the course of the videos, you can also select for the option to have an on-the-fly reprojection. And on-the-fly means it will only be in this project for that specific layer in this project, but otherwise the data file will not be changed. So I could open a layer now that may be set to a Universal Transverse Mercator projection system, but I can make sure that it will on the fly be reprojected into our Dutch grid, so I can still use it. So you can set these coordinate reference system options to your liking, and I don't mind to use the CRS from the first layer edit. Now, as the last file type that I want to demonstrate how to open it in QGIS, I want to use a data type that is typical of archaeological projects, such as a file containing measurements from a piece of survey equipment like a total station or GPS or what have you. And this is data which is stored as single coordinates, and these are typically stored in a text file or in the so-called file comma separated value file, which is actually the one that I have here. So ZV13 to plottenvondsten.csv. So these are individual finds that have been located using probably a total station system, and this file consists of individual coordinates, and I will show it in using the Windows Explorer first, so you have an idea of what's inside. So if we go to the Windows Explorer, I am here in the folder with the training data, and you can see here the same .csv file, and if I open it in a text editor, you can see how a CSV file is constructed. So you have here a first line containing the names of the columns. So these data you have to see as columns which are separated by commas, hence comma separated file. And so here you have the first column, which is called put, which means trench. And then you have a separation of the comma, and then you have vlak, which you could translate as layer. And then you have another comma, and then the third column would be type, and so on and so forth. And then in the actual data, so the rest of the whole file just contains data. You have here the value, so this would be trench 1 and layer 1, and then the type is a find, and so on and so forth. So this is the way that a comma separated file actually resembles a database table of systematically ordered data. And what is of course important for us to being able to import it in GIS is that here it has an X coordinate and a Y coordinate, and they are actually stored here. So here we have the X coordinate, comma, and the Y coordinates. So this is how the comma separated file looks if you open it in a text editor, and I will now show how you can import it into QGIS. So to open it in QGIS, I will go to my Manage Layers toolbar that I added using the view and then toolbars. And I'm selecting the third option, which is add delimited text layer. So this is the plus sign and with the comma symbol. Now if I click on that, I can select the file, so I have to browse to the right file, and then you can see that I can open the .csv file. I open it, and then we are confronted with a series of options. Okay, so the options here allow us to make sure that the data is imported exactly in a way that we want it to be. And we will always see the result of our choices here in this little window that says sample data. So here it shows the effect of your choices. And one of the most clear, the best example to show what happens if we change something. So it's now set to comma separated value. So that means it already makes the correct segmentation in different columns. But if we would say we'll use a custom delimiter, you can see that we would have totally different data. And actually, in no case here, except the comma, we would have a useful delimiter actually. Now, what is good to know, though, is that you can use this to create, if you have a file that is organized differently, for example, using tabs to separate your data, then you can use this file format section to make sure you set the right delimiter and import the data nonetheless successfully. And here I just selected for the others a quote sign that now actually puts everything within quotes in different fields. And you can see that it creates a big mess, so this is not what we want. So we'll just keep it at comma separated values. Now then we have a few options relating to records and fields, of which the most important thing here is to indeed have selected that the first record has the field names. We want to have an automatic detection of field types, which is a good thing. And we don't want any header lines to discard, etc. So there's a range of options that you can set here. We have a geometry definition in which we can set which field actually stores our X and Y field. So we have point coordinates instead of well-known text or no geometry. Then you would just import an attribute table. And here this is already correctly selected because it, of course, queries for terms like X and Y. And then finally, we have to set a projection, and this again refers to, okay, so you have coordinates, but how do I have to interpret these coordinates to make sure your data appears at the right location in relation to your project data? And of course, we set this here to EPSG 28992. Finally, there are some layer settings which are not really interesting for this introduction. So if I now click on Add and then close, our point data should have been added, and it is. So the finds actually do now appear within the excavation trial trenches, which is as it should be. Now, in addition, you can see that the layer appeared. So this is now another vector layer, and you see that the vector icon, actually the symbol changes according to the geometry type. So I have here verharding and spoor art, which are two polygon layers, which are indicated by this square polygon, and then for the finds, which are point geometries, I have here a point. Okay, so you just saw me also zoom in using one of the navigation buttons, and this is a good moment to explain a bit more about navigation through your map canvas. Okay, so you've just seen me use this zoom in button. We can of course use the zoom out button, and then you will draw a rectangle and the inverse zoom will be applied. You can use which is a very useful button in the navigation toolbar, the zoom last function, which by hitting it you go back to your previous view setting, which I use a lot. And then you have here the pan map. So if you select that, you can pan over your map. And it's very important. I think these are the most used navigational buttons, and I think it's very important to know that you can also do this navigation by either scrolling up or down your mouse wheel, or pressing your mouse wheel, hold it pressed, and then drag your map. So that is the same panning functionality as you have here. Now there are a couple of other functionalities which can be used for zoom to selection, or zoom to layer, or zoom to the full extent of your data. Okay, so in the meantime, we have here now 4 layers in our layers panel. And just to show how you can use that layers panel, apart from accessing your individual layers, is you can also change the order of these layers in order to change the order of your data in your canvas, in your map canvas. So let's say I would drag the layers 4 are below the digital elevation model. You can see that the data of this 4 disappears, or in other words, actually doesn't really disappear, but it's projected under the layer HN3 uitsneden. So this is just to show that there's a direct relationship to the order of your layers panel and the order of visualization in your map canvas. Okay, so now I showed the basic functions of GIS to open data, to different types of data, to navigate through your data, and to work a little bit with the layers panel. And we'll now go on to the part where we'll start asking simple questions to your data. Okay, so one of the most straightforward tools to ask questions to your data is to use the Identify Features button that you can use to click on any feature in your map canvas and assess the related information to that feature. So if we would do that, and an important thing here, which is different, for example, than in a software package such as ArcGIS, is that you select first the layer that you want to query. So I want to know something about the actual features in the trenches. So I select the spooraard. I zoom in so I see a little bit better what I'm doing. And I will click on the feature, on one of the features that I'm seeing. So what I then see appear, I will zoom in a little bit, is an Identify Results panel in which I will get the results of the features on which I clicked. Now these results are actually data stored in the attribute table, which is a concept I will come back to shortly. But if I enlarge a bit this column over here, you can see that these are bits of information that we also saw already as related data to the points representing finds. So we have put flag type, etc. Now this is a bit atypical GIS data, which is a peculiarity of this project, because usually you do not store overlapping polygons in a single layer, which in this case has been done. So we have here 2 features that I identified by clicking in the center of this smaller feature, I also automatically selected the larger feature that I actually didn't see as an outline of an individual geometry. So if I do it again, you can see that I see part of that layout here, but not totally. And this actually means that there is an overlap of features within this polygon file. And as I said, this is not a typical organization of data. You usually avoid overlapping polygons in a single layer, but there were good reasons for this particular project to do so. And this is why you see two features being identified, and the difference between them actually is that they are different layers of the same feature. So one is apparently situated deeper in the archaeological stratigraphy than the other one. In any case, what's important is that you can use thus this identifier to access this data. Now, of course, the same goes for the raster file. So if I would select the raster file, and we are actually now zoomed in close enough to see that these are indeed cells, regular cells organized in a grid that hold a single value. And if we would click on such an individual cell, you get here the information from the single band that it has, band 1, which is 8.68 meters above sea level. Now here you see also, apart from the data directly stored in the raster, also derived data. And in this case, the derived data, so this is spatial data that QGIS automatically generates from the project you're working in, and this gives us also the coordinate where we clicked. And to go back to the spoor art layer, if we would do this for the spoor art and we click again, you see here so the data stored in the attribute table, but you can also see here derived data, and then you get a whole range actually of geometrical data. So the area or the exact location where you clicked, but also the Cartesian area of the feature, the ellipsoidal area, and a number of others, such as the perimeter, so the total length of the polyline defining this polygon, etc. So you get the number of vertices, actually, so the number of points used to draw this spatial feature. So this is not data which is stored directly in your file or in the attribute table, but it is nonetheless data that QGIS automatically generates for you if you use this identify feature button. So you're probably wondering by now, what is this attribute table? So to get a little bit more into that, the attribute table is for vector data, a table that is connected to your layer, stored in your layer actually. It is a flat table that for every individual geometrical feature in your layer stores attributes. So it's a flat table that for every element, every polygon or point or polyline or what is there is in your vector file has a single record storing information. Now you can open this attribute table by right clicking on a layer and select Open Attribute Table. And then the attribute table will open in a separate window, and here you can see all the individual polygons in this case with the attached data, which is of course has a similar structure as the data that you have made appear here through the identified feature table. So again, you have to put fact type, number, etc. Because it's exactly the same data. Now I want to show the direct relationship between selections in your attribute table and the layer in GIS. But in order to do that, I want to change the color of the layer because the selection color is actually yellow, and it makes it quite hard to see from a bit of distance which of these features are selected or not. Okay, so I'll come back later, of course, to editing individual layers or the visualization of individual layers. But for this example of demonstrating selections, I will quickly change the color of the fill of these polygons to something that is clearly contrasting with the selection color yellow. So I'll make them a deep dark blue. And now you can see that they will be easily visible. So if we go back to the attribute table and I would now select a range of records, you can see that they are actually visible now here in the map as a selected set of features. Now this also goes the other way around. So if I would select features in the map like this, so this is for this I'm using the select features by area or single click, and I would go to the attribute table, then I have a whole range of features selected, which are an enormous amount because I have all these little stake holes, actually all these little wooden stakes for which individual features have been identified in the field are drawn, and so they are all selected, and that means that I have an enormous number of features selected now in the attribute. But the important thing to understand is that it goes both ways. So what you select in the attribute table has their geometric entities representing them in the map, so you select those, and if you select those, of course, the corresponding records in the attribute table. Now the attribute table has a couple of more interesting features. I will hit this button, deselect all, to, as it says, deselect all. I will not go extensively now through the editing possibilities, but you can toggle editing modes. And if you do, you are able to change the values of individual fields. QGIS also always works with editing modes because theoretically it is possible to have this file on a server, multiple people accessing the file or using it at the same time, and then if someone turns on the editing mode, someone else cannot do that anymore, of course, to prevent data corruption, because the file is being changed in different ways at the same time, which is of course a problem. Now, a couple of very useful options are the select features here. So you have select all, invert selection, deselect all, use a form, pan and zoom to the selected rows, which is very useful if you have, like here, a big extent, many small features. You can just select features in the attribute table and then zoom directly to them using the button. But maybe also a very interesting and useful tool to explain a bit more on is select by expression. Okay, so if we we open the select by expression tool by clicking on that button, we see the select by expression window that actually allows you to draw up an expression using existing operators, and well, you can do a whole range of selection queries using this window. And a very useful, very fertile thing to do is to be able to work with the actual data in the attribute table. So if I would, for example, click on fields and values and then on spoorart, so that would be the interpretation of the identified archaeological feature, you can see that two things happen. So I double clicked on Spoor Art, which means that here in my expression I will have Spoor Art as a field selected. And we could now, for example, enter the equals symbol and then select for all records that has a specific interpretation in its field Spoor Art. Now I can here now give a search term, but I could also, lower right part of this select by expression window, ask for all unique values that have been entered into the field Spoor Art. So if I click on all unique, I get a whole range of values which are actually the unique values entered into the field Spoor Art. Now if I would, for example, select slope, which would be a water-filled ditch, and of course this is a water-filled ditch that has been there in antiquity and isn't anymore, and I would double click on it, you can now see that the value will actually be entered as a selection criterion. So we'll now select for all records that have the term slot, so a small water ditch, registered in the field Spoor Art of the record. Now, and if I then select features, I close and I zoom to the selected features, we can see that a range of features actually show up, and in this case you can see that it's actually indeed a ditch that has been followed for an extended trajectory, and these are all the water-filled ditches that have been identified with this test range research. Now, in the attribute table you can see that I have a total features in this table of 2016, of which have been selected 110. Now, if you would for some reason be interested in what's more, for example, the periodization of these ditches, and you want to see them, but you do not want to browse through the whole table continuously, you have here a nice option in the lower left corner, in which you can switch between show all features and, for example, show selected features. So we can now only a list in the attribute table. So we deleted nothing, it's just a different view, a filter laid over our attribute table, and we now only see all the records that we selected using the expression. Okay, let's undo this. So I will deselect all. Of course, because we set the attribute table to show selected features, we do not see anything anymore. So I select again show all features. And a final useful tool in the attribute table that I wanted to show is actually the field calculator. And the field calculator can be used to change the value in a field or create a new field and automatically fill that field with information based on already existing information, again using all the different functions and operators that you can see here listed. And we'll be using this, but for now it is just enough to understand that if you would, for example, have two fields, one which is a field in which the total area in square meters of every feature is listed, and we would have another field with the total number of finds in that feature, we could use this menu to create a new field and fill those fields then automatically with a density. So have this area divided by the number of finds in that feature, and so we would get a number of finds per square meter, for example. And that would be a typical use of the field calculator. So you can do very advanced things with this and all kinds of calculations. And it's good to know that it's here. So as the final part of this first half of the introductory screencast, I want to show how you can select a subset of data based on the attributes in the attribute table and then save it as a separate shapefile containing only the features selected by your query. Now I will base my query on all the features that have been identified when the test trenches have been opened. And in Dutch archaeology, the first level encountered when you open up an excavation trench is typically called vlak 1, so vlak 1, let's say, translated to layer 1. And if you remember, looking at the attribute table, we have here the trench numbers and then directly after that layer numbers. So I just want to select from all the trenches only the first layer, so we will not have any overlapping features that have been identified on subsequent layers. Now, in order to do this, I will use a selection query, and I will use the selection toolbar in the main QGIS interface instead of the attribute table, which you can find here in the selection and the identification toolbar. So if I choose for the select features by value, I click the arrow, I can select the option select features by expression. So if I then come into this familiar by now screen, I go to fields, I will say I want to have the vlak field, but I can also, just to show how this works, enter it manually. So if you know your expression, you can just type in the exact syntax that you want, and I can select all the features at vlak 1 in this way. So I will select the features and see if my query actually gave me what I wanted. So I can see that I have a lot of selections, of course, a lot of features selected, because almost every trench has a vlak 1. I don't know what these trenches without a vlak 1 mean, but probably it just means that the second layer is just lying on top of it, which is again a reason why you shouldn't insert these overlapping polygons in a single file. But as you can see here, indeed successfully we selected all the features at every first layer of every test trench. Okay, and now just to show that you can do much more with this select by expression, I will just, as a demonstration, extend the expression. So we have now already the selection we are working with. Now I can add to this by saying, for example, I only want all features from the first test trench. What I can then do is I can select these features. So I would be making a new selection, immediately cancelling the old one. I can add to the current selection, but then nothing will be added, of course, because these features will already be within my selection. I can remove it from current selection, so then I will get all features at layer 1, but not those from the test trench number 1. Or I can filter current selection, and then I would get only all features at layer 1 from test trench 1. So if we would do that, and I would close, then we'll find here the features from indeed test range 1 and the first layer. Now, of course, we can also just do this in a single expression. So if we would type put one and, so we use the operator and then we would say vlak equals 1. I would have the same result, but then I would have this result as a result from a single query. But this is just to show that this is possible. So I will now go back to my initial query and just select all the features at the first layer. There we go. And what I now want to do is I want to save these features into a new layer. So I actually want to separate all these features at the first level, at the first layer, from this this file in which all these layers are combined. So QGIS makes this process actually very simple. So you right click on the layer. Here you can select export. You can then select save features as, but in this case we obviously want the second option, which is select save selected features as. So if we do that, we come into this window. In this window we have several options. Well, I like to work with the Shapefile standard, so I will select that one. I can of course enter a location and a file name, so let's do that. So I will make this, I will copy the file name of the, let's say, the source file, just to have a clear reference to where this data is coming from. And I will then say all trenches layer 1. I will save. I will then choose the CRS. So this is again an opportunity to save the features in a different coordinate reference system, and then they will be transformed to a different system. So if you would want to change your data, reproject as it is called, you could easily do this just by saving a layer in a different coordinate reference system. And then you have some technical bits about encoding and geometry type, but we can leave all that as it is. So if I now hit OK, it makes the export. It immediately adds this export to our layer panel. And if I then switch on the all trenches layer 1 and switch off the origin file, you can see that we indeed made a subselection of features that are actually just belonging to this first layer. And here we can double check, show select features, and indeed I now only have all the features at plug A. So in the second part of this introductory screencast, I want to address how you can do basic visualization of GIS data in QGIS. And in order to do that, I want to use the features, the shapefiles with the archaeological features, to show how you can give colors to different polygons based on classifications that are stored in the attribute table. I want to show how you can visualize the raster data in different ways by setting a color ramp. So color values are being distributed over the elevation values present in the raster file. And finally, I want to use the point file to show how you can put labels on the map. Okay, so in order to visualize the archaeological features with different colors, I will go into the properties window of this particular layer. So I select the layer with the right mouse button and I select properties. Now here we arrive into a window in which we can set a whole lot of options for this layer. For now, the most important ones being the symbology options. And if we select this, we can see here in the uppermost selection field in the combo box, we can select, we can hit on this, we can click on this arrow, and we can see that there are various options for the visualization of the data in this file. Now, the one that is currently used is the single symbol option. So what it gives you is a simple fill, and just very quickly you can click on these different layers to change the specific attribute. So what you can change is you can choose a layer type, a symbol layer type. So in this case we'll have simple fill, but we can also have a raster image fill up these features. We can have a gradient fill, a line pattern, but the most important thing to understand is that whatever you set here, all features will be similarly will have the same symbology, so they will have the same color or the same raster image or whatever. So, and then for these fills, you can select the color, you can select the fill style, you can select the stroke color, the stroke width, and so on and so forth. So you can virtually set almost any relevant option. What's more interesting usually for vector data, which, as I said earlier, is usually discrete data indicating different classes of information, or information classified in different categories. So, for example, roads and houses and whatever. And in this case, we have archaeological features, so they will be classified according to their interpretations. And so there are a range of other ways you can visualize and classify the data and visualize the features, but the one that you will use the most is the categorized option. Now, most important in this categorized option is to select the column on which you want to base the classes. So in this case, we can of course select all the different columns in the attribute table. So these are all the columns in the attribute table. And in this case, we want to select Spore Art because that is where the interpretation is stored. So if we select that and we hit classify, we can see directly all the individual features, all the individual interpretations of the features as they have been added to the column Spore Art. Now, it's interesting to see that there's, apart from every individual interpretation, there's also an empty field over here. So apparently there are fields in which there has been there's been entered no interpretation, and they will be given this this green variation, this color green variation. What you can also do here, if you would not want to visualize these at all, you can just click on the tick box and it will not visualize. And then maybe interesting to know is that you can here shuffle the random colors. You can double click on the color symbol to set specific colors if you want to make your own classification. And there are, if you select the color ramp, you can also select other preset color ramps, for example, to have your different visualization. You can also make your own color ramps by adding colors, changing the stops between the colors, what have you. So yeah, you have an enormous amount of freedom creating your own style for the visualization approach. So I will leave it at this for now when it comes to the visualization of the data. I will click OK, and then you will see that indeed my features are now colored according to their classification. So this is a laag, so it's a specific stratum. Here we have a slope, so water-filled ditch, and so on and so forth. So this is a ditch. Yeah, so now we have a consistent classification of all similar features appearing all over our map. Now, another interesting thing to point out is that we can now also assess this classification directly in our layers panel. So if we click on the arrow to unfold the information in this layer, we now see that we see the same classification appear here, and we can also now individually switch on and off various parts of this various interpretations here. So if we again would deselect slope, so a water-filled ditch, they actually disappear from the map. Okay, so when we then go on to visualization of the raster data, that is a bit of a different process, in the sense that not being discrete data but continuous data, visualizing information from a raster, at least when it's not a photographic depiction built up with RGB or similar values, but when it's a let's say a continuous variation of a variable such as elevation or slope or aspect or whatever, you will base your classification on a statistical analysis. There are no discrete classes that are, let's say, have their own logic. You have to impose this logic on the data, at least much more obvious and active than you would with the interpretation of archaeological discrete features. So the important thing to realize for visualizing raster data is that this is based on decisions you make. That is actually a classification that you impose, and it is therefore already part of using a GIS environment as an analytical tool. Obviously, based on the decisions you make and based on the resulting classification, you will maybe see some features or some, let's say, more elevated bits of your terrain better than others. So already you are making their important decisions as to the visualization and therefore possible subsequent understanding and interpretation of, in this case, your elevation data. Okay, so in order to engage with this, the visualization of the raster data, we go to a similar location. So we right click on the layer, go to properties, and again we have here the properties window with various tabs, and the third tab here is again symbology, layer symbology, and here we can select various options of how we want to visualize our data. Now at the moment it is set to single band gray, which means, and you can see this here in the thumbnail as well, we have a progression from white to black, or black to white in this case, where black is attributed to the minimum value and white is attributed to the maximum value, and there is a stretch of these values, gray values in between, going from dark to light. Now there are various options here. We can go for the multi-band color option, but then you see that you need to have at least 3 bands. So this would work if you would have indeed 3 bands in which you would have red, green and blue values stored. Now obviously we don't have that. Then you have paletted or unique values. This basically means that for an individual value in our single band raster, so for example 33, there is some kind of translation table in which this 33 is simply an index for a specific color code. So then you could use a raster to create still a complex image, similar to what a photograph, for example, could be. And then we have single band pseudocolor, and this is actually what we will work with the most when it comes to raster types like elevation models, because now we can actually treat the data similar as a single band gray, but in this case we select a color ramp that we can completely modify ourselves and stretch this color ramp over the single band values. Now the final option is the Hillshade option, which is a very nice one, which is an effect that you can add to the visualization of your raster, where an artificial light source is actually projecting artificial light over the raster, and the effects of shading are visualized in the raster. Well, this will come back in a later screencast, so I will skip that one here and just select single band pseudocolor. Okay, for the single band pseudocolor, there's a range of options you can set. So we can manipulate the min and the max values that we want to visualize, which means we could actually clip the values, so set a minimum and a maximum artificially to possibly leave out extreme values if we wish in our visualization. We can also do that by hitting this menu and use various options to cut off extreme ends, so to say. And we can choose for an interpolation. I will come back to these in a moment. And we can select a color ramp. So let's do that. Let's select a color ramp. Let's take, well, for example, the greens. And you can see when we select this, we immediately get a color ramp in which the various shades of green are stretched out over the minimum and the maximum values. We have here various modes: continuous, equal, interval, and quantile, saying something about the way these colors are distributed. And we can here add classes to the classification. But let's have a quick look at what happens if we accept this one. Okay, we have to zoom out a bit. We can see actually that we have here, let's say, extreme values, in the sense that we have here rather high altitudes in the field that are kind of skewing the color distribution, because we have these are very dark, and let's say the lighter stretch of the color ramp is stretched out over probably much more interesting variability in elevations that are now barely visible. So it is probably interesting to make sure that we filter out these extremes and see what happens. So in order to do this, we go back to the properties. Let's set the maximum at 12, for example, and maybe also to get a little bit more variation in the color ramp, because literally we are having here, let's say, a grayscale, but then instead of white on one end and black on the other, we have white and green, so it doesn't add much more variability to our color spectrum. So let's opt for one with a little bit more variation in color. So probably let's take this one, red to green, and then hit OK. And well, we can see here that now these very high elevations are all monochromatic green, so they fall all into this class 12, even the values which are higher. And that makes sure that we are now indeed seeing some more details in our map, and maybe even details that may be of archaeological significance, which could be true. We see, for example, here this water-filled ditch, and we also see a bit of a vague linear feature stretching out here that is apparently has an expression in the elevation values of the LiDAR data, and that may be, of course, something that has a connection. In any case, we can see here very clearly some lines that probably have to do with the old division in fields. But apart from that, it is clear, I think, that you can make different visualizations, and that, as I said, that immediately affects what you can do with the data and how you are able to interpret the data. Now, there are a couple of more things to know about this. First of all, we can, as I said, I will come back to do something with this interpolation. So now we have linear, which means that actually the color distribution follows a linear function from the minimum to the maximum value. What we can also do is discrete, which means we are going to enforce a discrete distribution of colors over these various classes. So what we are actually going to do is we are going to create classes here. So as you may notice with linear, this is just a value which basically is the midpoint for this color. If we would now set it to discrete, we can see that these colors are actually attributed to intervals of elevation values. So if we select this, you can see here that we lose the gradual gradient of the color ramp, and we get actually classes which are now visualized through a single color, which can be a way, of course, to simplify the elevation data in your map. And then the third option which we have here is exact, and now we can see that the value changes to equals, and that means that we have actually the colors now in our classification are attributed to the exact values that you see here listed. So only the exact value 7.624 now has the color red, which is in with this data, at least, of course, a useless way of visualization. So we'll just set it back to linear, and then again I cannot go into every detail of QGIS raster layer rendering modes. They are very interesting, especially the blending modes. So play with that all you want, but more to the point maybe for this introductory tutorial is that you can set here simple properties like brightness, saturation, or contrast with obvious effects such as increasing the contrast gives us an increased contrast between the various colors. And of course, again, that can help in analyzing specific elements in your data that may be better visualized with enhanced contrasts. Now, as a final demonstration of data visualization in GIS, I will label the actual finds. So the finds here are now indicated through these circular symbols. And what I want is to visualize the number related to that find. And I want to do that based on the information present in the attribute table again. So in order to do this, we go to properties. And maybe again, it's interesting to point out that for these markers, we can again set a whole range of symbology properties. So we can change the color We can change, we have here some presets for a red dot or an effect drop shadow with a nice star shape, so we can click that, apply, and we see effect. And we can again make categories of finds. So if we would have finds of different kinds, we could, for example, if we would have special finds of different types of metal objects, we could classify them according to the type of metal object, and so on and so forth. So it's just good to know that we have here all the same possibilities of visualization, or let's say all the similar possibilities of visualization as with the other vector data. I will just keep it at a blank dot. And what I wanted to show is how we can label to it. So if we go to the label tab, the property window, we can hit the menu and select single labels, after which this menu appears, and then we choose for label width, and again we see here this drop down menu in which all the columns available in the attribute table is being shown. Now the last column is actually called fonts number, so that it would be find number, so we can select that, and then we have here yet again a whole range of properties that we can set. So we can change the fonts, we can change the style, we can change the size, colors, whether we want it to be fake, and so on and so forth, formatting, buffers, backgrounds, etc., etc. So you can do here basically everything to make a very professional looking map. But in this case, I just want to demonstrate how you can make a functional. So I am happy with this settings for the appearance of the labels, and I click OK, and there they are. So now I have these black dots, apparently with a white outline, and I have the find numbers here present as labels. Okay, so now with the visualization of the data from the polygon layer, the archaeological feature layer, the raster file with elevation data and sorted, separated value file with the find numbers visualized as labels. I've come to the end of the visualization part of this first screencast, and to end this screencast, I want to mention, very quickly elaborate on two things. First of all, how to make a quick map, and second of all, how to deal with your project management. Okay, to start off with then the making a quick map. QGIS has a component called print layouts or layouts, and we can access these through the menu option project, and then go to print a new print layout. If we would already have made some print layouts, we would be able to select them here, but we need to start working on one, so we do new print layout. We can enter a title here. If we generate a title and we make a, let's say, a template for our layout, we can then subsequently use that template for different maps. In this case, I'm not really interested in this functionality. I just want to create a new print layout to generate a quick map. Now, then we come into this layout composer. What's important here to understand is that what we are now looking here at in the center is not anymore our map canvas, but is our page canvas. So this is actually the page as it is going to be printed. And in order to start working with this, we need to add all kinds of very different components to it. Now, the main component is going to be the information from our map canvas, and we can add that through this button over here. Adds a new map to the layout. So if we select that, and we drag a rectangle over our map, we can indicate the area in which we want the information in our QGIS map canvas to appear. So in this case, I just want maximum of the layout dedicated to the information in the map canvas of QGIS, and you can see that if I drag this rectangle, then within the rectangle, the current view of data in my QGIS canvas will be visualized. Now it is important to know that the zooming and navigating now can either revert to the information in this this component of our layout containing our map information, or related to the page. So if I select these navigation options like zoom in here in the top, or I navigate, what we are actually doing is we are navigating over the page, over the layout that is eventually going to be printed. Whereas if I would want to navigate through the data in the map, I need to select this option here at the left, move item content, and then I can actually move the data within the map component added to the layout. And if I use the mouse button, I could also zoom in and out of this data. So let's say I just want to make a very general overview of our project, so I can just use very far zoomed out version of our data. Okay, so as you may have noticed, this map actually also appears as an item in our table of contents that refers to all the components that we added to this particular layout. Now, in order to make this into a complete map, we want to add a scale bar and a north arrow. We can do that by using the buttons here to the left. So we have here the scale bar button, which we can click on, and then we drag a rectangle in order to add a scale bar to our map, which is immediately formatted to indeed reflect the true scale. Now, in the table of contents, you see the scale bar appear. I will not go into all details about how you can format these various items that you insert into your map, but I do find this a bit small, this scale bar, so I'll very quickly go into item properties and add 2 more segments to make it a little bit bigger and have a proper and useful scale bar. Now then we will add a north arrow, so I will do that by selecting the north arrow, or arrow actually it is, and we can make it into a north arrow by clicking on our map and then hold shift and go northwards. So it will make a straight line northwards. Click again left and then right click to finish it, and so we have a north arrow in our map. And finally we probably want to insert something of a legend. Now in order to do that, we have the function over here, the button to insert a layout, and we can again drag a rectangle over our map layout, and then we will have a legend in which all the items of the layers panel is added, all the information visible in our map canvas with all the relevant classifications. Now in this case it is way too big, so let's say that we just want to have the elevation values as part of the legend, because we just want to point out some of the potentially archaeological features visible in the elevation model, and then we can go here, for example, to the legend items, we do not want it to auto update, but we want to throw out everything that is not to do with the raster data classification. And now we just have the AHN3 elevation values and colorams attached to them. And then we have a very simple map. And we want this very simple map to export as an illustration. And we can do that by hitting layout and then select export as image. But as you can see, you can also export a scalable vector graphic. You can export PDF, etc. But we will go for the option of exporting a folder, an illustration, and we want it in a JPEG format. We are fine with calling it temporary. So we'll hit save. We will accept all these default settings and save, and then indeed we see that in the appropriate folder we will have the image appear, which is going to be this one, temporary. And indeed we have our proper map as we just designed it as the JPEG image. Okay, and then for the final issue, when it comes to project management, and I will return to QGIS for that matter, there are a couple of things to say, about which the first is by far the most important, and I will demonstrate the importance by saving the project. So I will select project in the menu, select save as, browse to the appropriate location on my hard disk, and in this case I will save this QGIS project as a file called project.qgz. Now I will hit save, and I want to replace it indeed. And if I browse to this location on the hard drive, and I can see here the actual project file, the most striking element here is that it's only 15 kilobytes in size. Now, why is this? A QGIS project file does not contain all the data that is shown in your project. What it actually contains, this project file, are all the references to the data file. So it contains a reference that on this or that location on your hard disk there is this file called AHN3 underscore uitsneden, and in this project we set this color going from red to green, stretched out in a linear fashion over all the values, clipping at maximum 12 levels, 12 meters above sea level. So that is what is being stored in this project file. So references, classifications, and manipulations, selections, or what have you on your data, but not the data itself. And that's of course important, because if you would send someone a project file such as we just made, without any of the accompanying data, then he will just have an empty file in QGIS telling him that he cannot find all the layers that are actually being visualized and used in the project. Okay, the next thing to say about that then is to point out that you can set, or that actually these days in QGIS your project is already set to relative paths. I will show you where this is done, where you can find the settings. So if you go to the menu project properties, you can see here that with general settings you have save paths as relative paths. Now, why is this important? This is important if you would want to replace your project. So you send your project with all accompanying data to someone else, or you just, in this case, in my case, all my data is located on an internal drive called Marmora, which is being executed to drive letter F by my laptop. So if I would change my external disk to a desktop and it would, for example, be attributed drive letter E, then the actual location of my data as an absolute path would be different. So it would not be F here, but it would be E. Now the same goes, of course, for when you send someone else your data or at a location suitable for him or her. Therefore, using absolute paths is very inconvenient, and these days it is default set to relative, and that means that QGIS will start looking for the referenced data files in the folder starting at its own location and any folder lower in the folder structure on your disk. So if you keep everything within that structure in its place and set your project to relative by default, you will always, QGIS will always automatically be able to find the relevant data. Now and then as the final note on project management, I have here this folder in which I have, well, let's say such few data files that I just threw everything into one and the same folder, but it may be obvious that if you have a lot of data organized or a lot of data in your project, you want to have that organized properly. For example, making a thematic classes such as topography, archaeological elevation data, aerial photographs, etc. Or you can organize it by data type, so you can make a folder for vector data and for raster data, etc. But it goes without saying that if you have a lot of data, you benefit from having it properly organized on hard disk as well. And think about that before you start a project. So once you start storing data files, your relative paths will always be kept in order and respected, and your project will always open references actually pointing to the data files properly. So with this final bit about project organization, we've come to the end of this first screencast in which I've introduced the basic data opening, editing, making maps, and a bit of project management of QGIS 3.4. Thank you for listening and watching.